Now, because we're going to find the universe is made of many different kinds of particles, it's important to classify them. There are many different ways we classify the particles. The first one I want to talk about is fermions versus bosons. I've talked about this a little before, but the difference between a fermion and a boson has to do with its intrinsic angular momentum, or spin. So just like we had orbital angular momentum with an angular momentum number L, such that L squared was equal to L plus 1 times h bar squared, and the z component was equal to m sub L h bar, where ml could run from negative L to positive L, counting only integers. We have an intrinsic angular momentum associated with the particle itself, as if it were spinning. It doesn't actually spin, but it has this angular momentum. And as before, it's classified by a quantum number s, such that the angular momentum squared is s plus 1 times h bar squared. But what's different, and the z component is just ms times h bar, running from positive s to negative s. But what's different is that now s doesn't have to be an integer. L was always an integer, but s can either be an integer, 0, 1, 2, etc., or it can be half integer, 1 half, 3 halves, 5 halves, etc. So the fermions are all the particles for which the spin is half integer, and the bosons are all the particles for which the spin is an integer. Then, most fermions that we're going to deal with are just going to have spin 1 half, right here. As we see, that gives us the possibility of being either spin up or spin down. And we talked about this a little bit when talking about electrons, that they could be spin up or spin down, and that's why we had 2 states for each orbital that an electron could be in. But perhaps the more important difference between fermions and bosons is that fermions obey the Pauli exclusion principle, which states that we can't have 2 identical fermions in the exact same quantum state, whereas bosons don't obey that principle. You can put any number of bosons you like in a single quantum state. I talked briefly before that this is because when you have identical particles, if you have a probability of finding particle 1 at position x1 and particle 2 at position x2, that's got to equal the probability when we switch the positions. Well, that means the wave function of x1, x2 has got to equal plus or minus the wave function when I switch the coordinates. Well, bosons take the plus. Fermions take the minus. And because of that, it's simply impossible to have a non-zero wave function where the 2 particles are in the same state. If I have the wave function for particle 1 is phi 1, and the wave function for particle 2 is phi 2, I need to anti-symmetrize this. In other words, I don't just leave it in this form. I make it minus the same 2 wave functions with x2 and x1 flipped. Excuse me. But if these 2 wave functions are the same, this would just end up equaling 0. For bosons, I would have a plus here, and this wouldn't equal 0, and I have no problem. But for fermions, switching the particles introduces a negative sign into your wave function, which means that you cannot have a wave function where both particles are in an identical state. It simply doesn't exist. That's a strictly quantum mechanical effect, but it has huge important repercussions. The fact that electrons are fermions and obey the Pauli exclusion principle is why we have chemistry. If all electrons could go in the same state, they would all fall to the 1s state, and all the different chemicals would behave in nearly identical ways. But because of the Pauli exclusion principle, the electrons have to fill higher and higher orbitals, and as a result, we get a wide variety of different chemicals. The Pauli exclusion principle is also why most materials, and metals in particular, are solid. We can't put multiple particles in the same state. It's why white dwarf stars and neutron stars don't collapse. And so you see it's very important. But other materials are bosons. One case of a boson is the photon. And in a laser, you put many different photons in exactly the same quantum state, and that's how we get that intense, coherent light beam. We can do it with pairs of electrons, not with individual electrons, but I can pair a spin up and a spin down electron. They become what's called a Cooper pair, and they can move through a superconductor without any resistance, because many different pairings go into the same ground state. And this picture shows the momentum relationships for rubidium atoms, which happen to be in a Bose-Einstein condensate. When they're not in a condensate, we have a lot in this central momentum state, but not a huge number. As the condensate forms, we get a macroscopically large number in that condensate. And this is known as a Bose-Einstein condensate. A macroscopic number of the particles condenses into a single quantum state. They first managed to make an atomic Bose-Einstein condensate like this in 1995, and it's kind of exciting for me because one of my friends from college was one of the people that worked on forming such a Bose-Einstein condensate.